Alright, hey guys, and welcome back to another AP Physics C electricity magnetism video. This is a major derivation. Today we're going to be doing the electromotive force, the induced EMF, in other words, on a square loop of wire from a current that is going through a wire that is pointing to the left. That's changing with respect to time. So let's just jump right into it. This derivation, we see that the current is given to us as a function of time I naught t. There's a distance d from the conducting loop to the wire, and the conducting loop has width w and length L. So in this instance, really what you need to be thinking is whenever we have an induced electromotive force, we need to use Faraday's law, right? Faraday's law dictates that the electromotive force is equal to the absolute value of the negative derivative of flux with respect to time. And you might be thinking, well, shouldn't that just be the derivative of flux with respect to time? Won't the absolute value just cancel it out? It doesn't matter. The reason why this negative is there in the first place is because of Lenz's law. Lenz's law states that whenever you have a change in magnetic flux, a system will try to oppose it, right? So this loop of wire is really trying to oppose the change in magnetic flux by generating a current, right? Generating an electromotive force that generates a current that will replenish the change in magnetic flux. So if it's increasing, it'll make it decrease, right? If it's decreasing, it'll make the flux increase, right? The flux wants to stay the same. That's why that negative is there. The reason why I'm adding the absolute value, which sometimes AP Physics C will ask you to do, is because I want the magnitude. I don't care about whether it's replenishing or whether it's diminishing. Um, all I care about is the magnitude. So that's what we're going to do here. Now we need to realize that I have flux through this loop, but I don't know exactly what the flux is because the flux varies with time. And in this instance, we're going to look deep into this image. The flux also varies with radius, right? Here's a radius r. And this r is, let me move this. This r is a distance, the distance from the wire to a little point dr along the width of this loop, right? So this dr is an infinitely small change in the radius or the width of this loop, which corresponds to a dA, a small area of this loop, right? But what we need to realize is that the magnetic flux will vary along this entire width. So the magnetic flux here, I'm going to use that in pink, might be really strong, right? But it might weaken. It might weaken as we get further and further from the wire, right? It gets tinier and tinier. And the reason why it gets tinier and tinier, I'm going to write this now before I forget, is because the magnetic field, B wire, due to a wire, is inversely related to current, right? It's 2 pi, it's mu naught I over 2 pi r. So if I increase radius, right, if I get further away from the wire, I get less magnetic field. The magnetic field is less strong. So that's really how this is going to work. So we need to realize that the radius, wow, well, it varies along this entire wire, starting from a radius of d, ending at a radius of d plus w, right? And really, all you need to think here is, well, how am I going to get the total flux if the flux varies? This is where the integral calculus definition of flux comes in. So I'm going to derive two ways to get to that definition. Did I? Okay. Two ways. So this is flux, and we want as a function of time. The reason why this function of time is there, I'll explain it later, but for now we're just going to treat it as if we're finding flux. So flux, the technical definition is B dot A, right? But the calculus definition is the integral of B dot dA. And how we get there is we know that in calculus, if we integrate something like dx, that'll just give us x, right? If I integrate dq, like for charge, that will just give me q. So if I integrate dflux, that will just give me flux, correct? So now we need to realize, well, what if I sub in the technical definition for flux inside of this integral dflux? Well, then this will become the integral of dB dot A. And in this instance, we need to realize this R, I'm going to pick it up, it stays the same so long as we're focusing on the same dr over the entire length L up here. This length is a constant, right? So this R will stay the same for this entire dA along this entire L. So along that dA, the only thing that is varying, the only thing that we need to measure the infinitely small change in, right, is the area, because that's what we have. We have a dA along because the r is constant, the magnetic field will be constant because the magnetic field is not dependent on the x position. It's only dependent on the y position, or the distance away, the radius, right? So the only thing that's changing is not the magnetic field. So we can pull the magnetic field out because it's a constant. And now I get this integral, right? And I'll simplify that. The only thing that's changing is area. It's an infinitely small change in area. So now I get this integral b dot dA. And you might be thinking, wow, wait, it's the same thing. It is the exact same thing that we had before. So that's just another way to get to it. That's an intuitive way to think about it. I'm going to say one last thing about that, and then we'll move on. So the intuitive way you should be thinking about it is, I'm going to move this dA. We're basically integrating from r equals 0 along this entire thing, along all of these r's, along this entire loop, right? Until we get to the top. Infinitely small dAs that have infinitely small correspondent d fluxes, right? So we have infinitely small changes in area that have infinitely small changes in flux that we integrate in order to get the total flux, right? That's where the integral calculus comes in. That's why we use calculus, right? Because when we have a dr that's so small, we can say that it's a point, and the magnetic field at the point is given by this equation, right? And it can be treated as constant along this entire length, because along that entire length, the radius, the distance from the wire is the same. So now we're going to use this definition in order to find the flux as a function of time. So we're just going to start by evaluating that dot product. We're going to do B dA cos 180, right? Because it's the magnitude of the two vectors times the angle between. And the reason why it's 180 is because the magnetic field points into the page, but the area vector points out. So the magnetic field I'm going to draw in pink, and the area vector I'm going to draw in black. The reason why the magnetic field points in, right, is if you take your right hand, this is called the right hand rule, and you point your thumb in the direction of the current. We know the direction of the current is to the left. You curl your fingers, that's the direction in which the magnetic field points, right? So your fingers curl in when you do that. So the magnetic field points into the page, right? But the area vector points out. So the two vectors, when I look at them, they kind of look like this. If I were to look at them from the side, this is what they would look like. And the theta, the angle between them, is 180 degrees, right? So now cosine of 180 is -1, but because we have that absolute value on the top, I know I'm going to be taking the absolute value anyway. That -1, we really don't have to care about it, right? So we can just say that this entire thing will evaluate to 1, and now I get the integral b dA. But I need to think, okay, well, for that dA, what would be the magnetic field for that little dr along that entire dA, right? Along that entire length. And that magnetic field would be mu naught I divided by 2 pi r, which is the magnetic field from a wire, because if the radius is constant along that entire length, well, the magnetic field will just be this, right? Because that's the equation, that's a general equation you should memorize for AP Physics C. It's derived from Ampere's law, but yeah, point being, the magnetic field will be constant along this entire length for this entire dr, because the radius is the same. So now I'm going to do one small little change here. I'm going to say mu naught I of t. That's what I'm going to include, because the current isn't constant. It's changing with respect to time, right? And you might be thinking, well, I can't compute this integral because I have two things that are changing. I have radius that's changing, and I have current as a function of time. Time is changing. Not necessarily. You don't have to worry about that, because in this instance, time and radius are unrelated. So if time is changing independently of radius, I can treat it as a constant when I'm looking at radius, right? And constants, guess what I can do to those? I can pull those out of my integral, right? That's a bad representation. So I'm gonna pull those out of my integral in a bit, but here you can see where the b went. This is the b, right? And this is the dA. So now I'm just going to do what I was going to do and pull out the constants. I of t is outside of the integral because it's not related to r. It doesn't change with respect to r, so I don't have to integrate with respect to time because r is changing. We only want r in this instance. We only want to focus on our dependent variable r. So now I get this integral. right? I get mu naught I of t divided by 2 pi times the integral of 1 over r dA is going to give me the magnetic flux as a function of time. And remember earlier how I said, well, I get magnetic flux as a function of time, but I'm just going to treat it like it's just magnetic flux. The reason why I added this as a function of time is because the current is as a function of time. That's where the t variable will come in and give me an expression for magnetic flux as a function of time, right? That's the only reason why I added that, because it comes through here. It expresses itself through a changing current, which gives you a changing magnetic field as a function of time, right? So now I'm going to do one small little thing. This current was given to us as an expression, I naught of t. I'm just going to sub that in here and say I of t is I naught t, and now I get this expression. So now this right-hand side is what I need to worry about. I have this 1 over r dA, but I know that my dependent variable, my function that I'm going to try and integrate along, is 1 over r. But I have dA, but I know dA is somehow related to dr, right? So I'm going to try and express dA in terms of dr so I can get an actual comprehensive integral. And there's two ways we can do this. First, we're going to do the visual geometric way. If you look here, we know that area expresses itself as length times width. And we know that the length here, right, is L. The area of this entire thing, big A, is length times width. Of course, that's just natural. They taught you that in geometry. But the infinitely small change in area is dA times dW, right? Well, you might be thinking, well, I don't see dW anywhere else but here, and that's d plus W. That's not an infinitely small change in W. You'd be absolutely right, because it's not dW, right? It's dr. And you might be thinking, well, wait, you just contradicted yourself. No, I didn't. Because an infinitely small change in width is the same thing as the infinitely small change in radius, right? So dA, this infinitely small change in area, is going to equal L dr. And that makes sense because the length of this entire small area is L, but the width here, you can see, it's dr. So that's where I get this expression, L dr, and that's where I can sub into my integral. But there's another reason why this works, right? And I'm going to show that over here. If I describe area as a function of that little radius, or a function of that radius r, I say it's L times r, right? Times red r. If I were to take the derivative of that arbitrary function, dA dr, I get dA dr is equal to L times, 1, right? Because if I take d dr of r, that gets me 1. If I take d dx of x, that gets me 1. That's just the rules of calculus. We don't need to worry. Oh, I copied it on accident. We don't need to worry about that. But now, interestingly, if I multiply dr to both sides, I get dA is equal to L. Guess what's going to be on the right side? dr. It expresses itself in both ways. The geometric way is just so you have that understanding of why this works. But this way, right, this is the easier way that you should be doing on the AP exam, as to not waste time, to show your reader that you understand why dA is equal to LDR. So now that I know dA is equal to LDR, I'll just sub that in on my integral, right? I'll rewrite my constants on this left side for 2 pi integral. Oh, that's a bad integral. That's a bad 2 pi, so I'll rewrite these. Integral 1 over r L d r. And I hope that made sense. Please let me know if you have any questions about that. But I know L is a constant, so I can just move that outside of the integral. And now I need to think, well, what are my integration bounds here, right? And we could have thought about these integration bounds way earlier. When I'm summing up all of these little dAs, I was moving this dA earlier. I'm summing up these little dAs along this entire width, right? Not along the length, along the width. And the width starts at this radius equals d to radius equals d plus w. So guess what my integration bounds are going to be? My integration bounds are going to be d to d plus w, right? So I'm going to put that down here, d plus w. And that should make sense in terms of radius as well, because the first dA we encounter, right, is at radius equals d. And you can also think, well, the first radius we encounter is radius equals d, and the last radius we encounter, right, the last radius that corresponds to a little dA, which corresponds to a little d flux, is d plus w. So those are our integration bounds. That's all we need to sum along. So what I'm going to do now is I'm going to evaluate this integral. If you remember, the integral of 1 over r dr is ln of r, right? And of course, it's a definite integral, so we have to go to d plus d, or d2d plus w. And now we'll keep these constants, mu naught, I naught, t times L over 2 pi. And I'm going to clean up this left-hand side a bit by using the fundamental theorem of calculus to evaluate all of these things. So ln d plus w minus ln d, because this is how calculus works, right? And I'm a little lazy, so I'm going to copy these constants down here. And now we're going to remember our rules of logarithms, right? So we know that ln b minus ln a is equal to ln b divided by a, right? So here, well, guess what? This is my b, this is my a. So this entire natural log expression consolidates to d plus w divided by d, right? Not much more needed said about that. And now I have mu naught I naught t L divided by 2 pi. And for simplicity, I'm going to move this t over here. I'm going to actually color the t in a different color so you guys can see what I'm going to do easier. So these two are the same expressions, right? I just moved the t to the front just for simplicity. This t was this t, right? These are the same. Hopefully you see that. And now, sorry, these lines are to show that these two expressions are not related. And now, this is my magnetic flux as a function of time. You see I have this entire expression, and then I have t to give me my as a function of time. So this is my magnetic flux as a function of time. As a function of time. And now I need to recognize that, well, Faraday's law told me you have to take the absolute value of the negative derivative of that. So that's what I'm going to do down here. So now I know the electromotive force is going to be the absolute value of the negative derivative with respect to time of that entire expression, which was mu naught I naught L. This takes a lot of rewriting, which annoys me. ln d plus w over d, right? And that entire thing gets multiplied by t. And now what you may realize here is, wait, all of these values are constants, right? Mu naught is a constant, I naught is a constant, length is a constant, 2 pi is a constant, ln d plus w over d is a constant. The only dependent variable in this derivative is t. So all of this, we'll call that one big constant times t. The derivative of any constant, we'll call it k. The derivative of a constant kt, right, d. This derivative evaluates to just the constant, right? Because it's a linear multiplier, t. So guess what? The same thing applies here. So the induced electromotive force will be mu naught I naught L over 2 pi ln d plus w. And I kept saying the derivative of a constant. The derivative of a constant is 0, but when the derivative of when you take the derivative of a constant times a linear multiplier, right, which is the dependent variable, it has to be the dependent variable, times, like, if it's 2t and you take the derivative, that's just going to be 2. That's my point here. This entire thing is a constant, so we can just drop the t and then bam, we get our derivative. So here we get mu naught I naught L divided by 2 pi times ln d plus w over d is equal to our electromotive force. That is our induced electromotive force, and that's all you need for this problem. So hopefully that helped you guys and it made a little bit more sense. But yeah, that is the entire derivation. It took a little bit, but we got there. Hopefully it made some more sense, because this is honestly one of the more difficult derivations. Not the most difficult, but definitely up there. So yeah, I hope this video helped you guys, and I'll see you guys in the next one.